Welcome to the deep dive. If you're in software, you know the feeling. It's this constant battle, right? Speed versus quality.
It really is. You're trying to ship features, get things out the door.
And then QA pushes back with a list of bugs.
Yeah.
It just feels like this eternal tug of war.
A tug of war where development and quality assurance are, fundamentally on opposite teams, adversaries.
Exactly. And that conventional wisdom, that adversarial model, is exactly what we are going to challenge today.
We are. We're diving into a philosophy that completely changes the objective. It flips the whole thing on its head.
So we're not talking about testing as just a net at the end of the process to catch bugs.
No, not at all. We're talking about it as the foundational architecture of the system itself. It's built in from the very beginning.
Our sources for this deep dive, they propose it's a seemingly paradoxical, almost shocking claim.
It is a bit of a shock to the system when you first hear it.
The idea is that the non-negotiable goal of the entire development group is for the independent QA team to find absolutely nothing.
0 bugs. And that sounds impossible, but it's a complete paradigm shift.
How so?
Well, if you actually achieve this goal, or even get close to it, it means you've built a system that's so robust, so verified at every single micro level, that it's structurally sound before it ever even reaches that final testing gate.
So our mission today is really to give you the blueprint for how to get there. We are going to deconstruct the test automation pyramid.
It's a really powerful visual. It's a structured hierarchy that dictates not just what tests you should write, but
how many and when you run them. It's a whole strategy.
Exactly. And if you're listening, you are going to walk away understanding why a handful of really, really fast tests are worth so much more than 1,000 slow ones.
And why quality is something you build in, not something you just test in at the end.
And we'll show how something like test-driven development, TDD, which a lot of people know about, is absolutely essential, but it's still only one piece of this much larger puzzle.
It's about prevention, not just detection.
That's the core of it. Prevention over detection.
Okay, let's unpack this central paradox, because this is where the whole philosophy pivots. Why on earth is the goal of the entire development organization that QA should find nothing? Isn't that like, I don't know, hoping your security guards find 0 breaches? Doesn't that mean they're not doing their job?
That's a great analogy, but the perspective is different here. It's an internal measure of success for the development pipeline. Think of the QA team as your external, unbiased audit.
Okay, like a third-party audit.
Right. So if an independent group of really intelligent people whose entire job description is literally to find flaws, if they can't locate a defect, what does that tell you?
It tells me the process before them was incredibly effective.
Exactly. It means the thousands of internal tests, the TDD processes, the coding discipline that the developers executed, it means all of that was successful.
So it's not about undermining QA at all. It's about raising the bar for developers. You're holding the development team accountable for shipping clean code before it even gets to that final check.
Precisely. The system must be verified. It has to be correct before it ever reaches that expensive, slow, high-level testing stage.
Now, we have to be realistic here.
Of course. Let's be very clear. This goal, this finding nothing, it won't be constantly achieved. Bugs are an inescapable reality. You have human beings involved. You have complexity.
But the goal itself, the philosophy, sets the standard.
That's incredibly high standard for professional discipline. It changes the conversation.
Okay, so what happens when the inevitable occurs? When QA does find something? If the goal is perfection, then imperfection must feel like a catastrophe.
The reaction has to be systemic. It can't just be, oh, another bug. When a defect is discovered by the QA group, the development team should react with what our sources call horror.
Horror. That's a really strong word.
It is, and it's chosen deliberately. Not frustration, not defensiveness, which is, the common counterproductive reaction we see all the time.
Right, it works on my machine response.
Exactly that. It has to be genuine shock.
But why horror? Why so dramatic?
Because the discovery of a defect by QA is viewed as a failure of the development process. It's not just a failure of a specific line of code. That horror should force immediate systemic action.
So you don't just patch the bug.
You absolutely do not just patch the bug. You must take immediate steps to prevent similar issues from ever occurring again. You fix the hole in the process that let the bug through.
So let's make that concrete. If QA finds, say, a null pointer exception because the user submitted a form without a required field.
Right.
The conversation isn't just go fix the bug.
No, the conversation is, Why didn't our unit tests catch this input validation failure? Or why didn't our component test scenario include this specific alternate path? It's a post-mortem on the process.
So it forces a critical self-assessment.
Precisely. You have to ask, was our test coverage adequate? Did we have the right coding discipline? And most importantly, do we need to introduce a new, lower-level test that specifically protects against this class of error for all future development?
I see. So you write a new test that would have caught this bug, and now that test runs forever, protecting you from that entire category of problem.
That is how you embed quality deep, deep into the organization's DNA.
And that completely shifts the culture. It moves away from that toxic adversarial model.
The one where QA and development are just throwing things over the wall at each other, requirements go one way, bugs come back the other.
Yeah, that's so common.
And it's counterproductive and incredibly expensive. They are part of the same team. They have to be working together to ensure system quality and prevent defects.
Because if QA is finding tons of bugs,
It means your feedback loop is slow. It means your developers are spending their time working on defects that should have been caught locally, minutes or even seconds after they were written.
and that's the true cost, isn't it? The delay.
That is the true cost of that adversarial relationship.
Right.
It's inefficiency at a massive scale.
Okay, so if QA is no longer just this final gatekeeper, this final bug finder, what are their new roles? Our sources say they have two main modern functions within this proactive quality architecture.
They do. They are elevated from simple testers to something much more strategic and critical to the project's success.
And those roles are?
They step into two absolutely essential roles, QA as specifiers and QA as characterizers. These roles completely redefine their value.
Let's start with specifiers. That sounds like they're active participants in defining the requirements, not just, validating the final product against some finished document.
That's exactly right. In the specifier role, QA works directly with the business stakeholders, with the product owners, to create the automated acceptance tests.
Okay, so they're writing tests.
They are, and this is arguably the most powerful change in the whole philosophy. These executable tests become the true specification. They become the actual requirements document for the system.
Replacing those 100-page Word documents that nobody reads and are out of date the second they're written.
Exactly. Those long, easily misunderstood narrative documents. You replace them with something that lives, breathes, and executes.
I love that idea. The requirement isn't a PDF that sits on a shelf. It's a living piece of code that tells the system what to do and proves it's doing it.
That's it. There is no ambiguity.
So how does QA actually facilitate this translation of business needs into code?
They lead that iterative process. They sit down with the business and they gather requirements. Let's say the requirement is a customer must be charged the full price unless they have an active coupon code.
A classic e-commerce rule.
Right. QA's job is to translate that narrative into a specific executable test case. They'll often use tools like Cucumber or Fitness.
Tools that let you write in something close to plain English.
Exactly. You see that given, when, then format. Given I have a product in my cart, and when I apply a valid coupon, then the final price should be discounted. The business can read that and sign off on it.
And it's directly tied to the underlying code.
It is. If that test passes, the business requirement is met. There is zero room for interpretation or ambiguity. It's either green or it's red.
But doesn't that put an enormous burden on QA? I mean, are they writing every single test case for every possible scenario?
That's a great question. The labor is actually split strategically. It's a partnership. Generally, a QA is responsible for writing the happy path tests.
The happy path being the main expected workflow.
The typical expected workflows that show the system fulfills its primary purpose. They are defining what success looks like.
Okay, so where do the other tests come from? The edge cases, the error conditions?
The developers. The developers are typically responsible for writing the detailed corner, boundary, and unhappy path tests.
Why push those negative scenarios specifically onto the developers?
Because the developer has the deepest insight into the code's internal logic. They know exactly where the input validation sits, what specific errors are possible, where the boundary conditions are.
Like what happens if you put a negative number in the quantity field or a string of text?
Exactly. Maximum integer size, empty input fields, all of that. It makes sense for the developers to use their unit testing discipline, their TDD, to rigorously safeguard the system against every possible failure mode they can imagine.
So QA defines what success looks like, and development guards against how failure can occur.
A perfect summary. That dual responsibility strengthens both roles immensely.
Okay, that makes sense. Now let's pivot to the second crucial function, QA as characterizers. This sounds less about definition and more about investigation.
That's exactly what it is. This role relies heavily on the discipline of exploratory testing.
Okay, and what's the characterizer's job here?
Their job is not to confirm if the defined requirements were met. That's what the automated specifier role did. The characterizer's purpose is to report back on the true behavior of the running system.
Especially under novel or unusual conditions.
Yes, they're observing reality rather than just confirming against a static plan.
So QA is now free from the confines of that initial requirements document.
Completely free. They're identifying the actual behaviors, the emergent properties, the unexpected interactions of the whole integrated system. They aren't asking, does this meet requirement 3.1?
They're asking what?
They're asking, if I click this button 100 times while the database is slowing down, what happens to the state of this user account? Or what happens if I open 2 browser windows and try to edit the same record at the exact same time?
So they are using their human brain, their creativity, their domain knowledge to push the system until it breaks or exhibits some kind of peculiarity.
Precisely. And this feedback is invaluable. It's where you uncover systemic weaknesses like race conditions, poor session handling, memory leaks, things that are virtually impossible to specify or automate beforehand.
It's the highest value use of a human's time in the entire quality assurance process.
But without a doubt, you can't automate creativity and intuition.
This all sets the stage perfectly for the blueprint we need to follow, the test automation pyramid. If we accept these new roles for QA and the goal of finding nothing, we absolutely need a structure that optimizes for speed and coverage.
And the test automation pyramid is that structure. It's the graphical depiction of this hierarchy. It visually represents the volume, the speed, and the cost of all the different test types you need.
Okay, so why is the pyramid shape so important? Why is it non-negotiable? Why must we have many, many small, fast tests at the bottom and only a few slow tests at the top?
It comes down to economics and, honestly, human psychology. It's all about the feedback loop.
Okay.
The wider the base of the pyramid, the faster and cheaper the tests are. The narrower the top, the slower and more expensive they are. If you invert this,
Which a lot of teams do.
they do. It's often called the ice cream cone or the cupcake anti-pattern. You end up relying on slow, integrated, high-level tests, usually UI tests, to give you your primary feedback.
And if my feedback loop is slow, what's the real damage?
The damage is exponential. Think about it. If a developer checks in code at 10 a.m. and your big, slow, high-level system test fails 3 hours later at 1 p.m.
The developer is completely moved on. They're working on something else entirely.
Exactly. They have 3 hours of new work, new context, layered on top of that bug, the context switching, the debugging time to even remember what they did, and then the fix itself. It's all exponentially more expensive.
Versus if the bug had been caught by a local unit test.
30 seconds after they wrote it, when the code is still fresh in their mind, the pyramid structure is designed to guarantee the fastest possible feedback to the developer.
So even with a discipline like TDD enforcing quality at the code level, you still need this pyramid hierarchy to validate the architecture, the assembly, and the performance under load.
Yes, TDD is necessary, but it is not sufficient.
How so?
TDD ensures the internal mechanics of your components are sound. The upper layers of the pyramid ensure that when you bolt all those sound parts together, the entire structure doesn't collapse or communicate inefficiently.
Let's break down the volume then, starting from that massive base. What are the numbers our sources suggest?
The ideal breakdown from bottom to top looks something like this. Unit tests should be targeting 100% coverage,
The whole base.
the whole base. Then component tests are about 50% of the test volume. Integration tests are around 20%. System tests are at 10%.
And at the very tip.
That tiny apex, just 5%, is for your exploratory and manual tests. That's the human element.
This is the structure that maximizes efficiency. The vast majority of defects must be caught at the lowest, fastest, cheapest level.
If they're not, you're paying a heavy price in time and money.
Okay, let's start at the bedrock then. Unit tests, the 100% base. These are firmly in the domain of the programmer.
Correct. They are written by the programmers using standard frameworks, like Jonah in the Java world or Unit for .NET. And they are fundamentally specification tests for the code.
And critically, as a principle of TDD, they are written before the production code is written.
That timing is everything. That's what transforms testing from a verification activity into a design activity.
It forces the developer to really think about the API, the inputs, the expected outcome, before the implementation is even considered.
Yes. It forces clean interfaces and single responsibility. If a unit test is genuinely difficult to write, that's often a huge red flag that the underlying code you're about to write has too many dependencies or is trying to do too much.
So the unit test itself serves as a check on the design integrity.
It absolutely does. And because these tests run in milliseconds, they can and should be executed constantly on the developer's local machine every time they save a file, and immediately as part of every single continuous integration, or CI, run.
Now let's talk about that coverage target, 100%. That can be a point of stress for teams. And we need to define what true coverage actually means, because developers can game the system, right?
They absolutely can, and this is a critical point. The goal is as close to 100% as is practical, but the emphasis has to be on true coverage, not just the percentage number that your tool spits out.
So what's the difference? What is true coverage?
True coverage means the test not only executes the code, but it also asserts that the outcome or the state change or any side effect is correct.
Can you give us an example of false coverage? The kind that looks good on a dashboard but is actually useless.
Sure. A simple example is a function that does three things. Let's say it's validate input, then process data, and finally log result.
Okay.
A lazy developer might write a test that just calls that main function. The code coverage tool will say, great, 100% line coverage. But the test might only have one assertion that checks the return value of validate input.
So it never actually checked if the data processing was correct or if the log entry was actually written to the log file.
Exactly. The code was executed, the behavior was never verified.
You've created a totally false sense of security.
A dangerous one. Tests that merely run code without asserting behavior are worse than useless. They're actively misleading. A professional development group will be ruthless in auditing for these gaps. The unit test base is there to specify and guarantee the functional intent of every piece of low-level code.
All right, that's a solid foundation. Moving up the pyramid, we hit the 50% volume mark. Component tests. What are we testing here, and why does the volume drop so significantly from 100%?
Component tests are essentially the acceptance tests, but they're written against individual, self-contained components of the system.
So if unit tests verify individual functions or classes.
Then component tests verify the business rules that are executed by a whole service or a module working together. The volume drops because you need many, many functions to build a single component, but you might only need a few component tests to verify the overall business rules that that component is responsible for.
Can you give us an analogy to make that clear? The isolation aspect seems really key here.
Okay, think of a car engine. Unit tests are like testing the internal components in isolation. The piston moves correctly, the valves open and close at the right time.
Got it.
A component test is like taking that entire fully assembled engine and putting it on an isolated testing stand in a workshop. You hook it up to simulated fuel and power from the stand, you give it input, you press the throttle, and you measure the output, like torque and RPMs.
I see. So the engine is running and doing its job, but it's not installed in the car. It's not connected to the real transmission or the real fuel tank.
Precisely. That is the concept of decoupling and isolation via mocking and test doubling. When we're testing the billing component that processes a credit card transaction, we pass input to it. If that component needs to talk to a real database or a real external payment gateway,
You fake it.
we mock those external dependencies. We create a fake payment gateway that instantly says success or failure without actually making a network call.
Why is that decoupling so crucial at this stage?
Two huge reasons: speed and isolation. First, speed. Waiting for a real network round trip to an external service or a disk write to a database slows down your test suite dramatically. If component tests are slow, developers just won't run them frequently, and they stop being useful as a fast feedback tool.
And the second reason, isolation.
Isolation. We want the component test to fail only if the business rule inside that component is broken. We don't want our test to fail because the external payment gateway's API is down for maintenance or because the shared test database server is overloaded.
That makes the component test a pure validator of the business logic, totally independent of the infrastructure it runs on.
Exactly. And this is where that QA specifier role we talked about really shines. This is their domain.
Defining what the business expects the component to do.
Yes. These tests are typically written by QA and the business, maybe using those BDD frameworks like Cucumber. It is absolutely essential that the business can read and interpret these tests to make sure they accurately reflect the requirements. The development team helps wire up the technical side, but the ownership of the intent lies with the business and QA.
And what specific paths are these component tests focused on covering?
They are heavily, heavily focused on the happy path situations, the 80% of transactions that go smoothly, and maybe a few very obvious corner cases that are core to the business rules.
But not every single error condition.
No, and this is a critical point from the sources. The vast majority of unhappy path tests, the detailed error handling, the input validation, that should already be covered by the hundreds of unit tests below them.
So component tests validate that the component behaves as expected, while unit tests validate that the component defends itself robustly.
That's a perfect way to put it.
That distribution feels very efficient. But let me play devil's advocate here. If QA is using tools like Cucumber to write these requirements as tests, isn't there a massive risk that those tests, those specifications, just become neglected, that they get outdated, just like the old PDF requirements documents? The maintenance overhead is real.
That is a critical challenge, and it's a valid concern. The value of these executable specifications, sometimes called living documentation, is only as good as their maintenance.
So how do you defend against that stagnation?
The defense is the frequency of execution. Because component tests are isolated and fast, they absolutely must be executed constantly, right alongside the unit tests, as part of every single CI build.
So if they're failing, you can't ignore them.
You can't. The build breaks. They must be fixed immediately. If a business requirement changes, the test must be updated before the code is touched. This rigorous discipline is what prevents them from becoming those dusty PDFs.
But that discipline relies on them being fast.
It's the key. If they run slow, they get skipped. They get moved to a nightly build. And that's when the rot sets in.
That's a really powerful insight. If your main CI pipeline, the one developers use all day, takes longer than, say, 10 or 15 minutes to run, it's often because your component or integration tests are too slow.
And that lack of speed immediately compromises the quality discipline of the entire team. Speed is not a luxury here. It is an absolute prerequisite for quality.
So we verified the code logic with unit tests and the isolated business rules with component tests. Now we start moving up to the vertical integration layers. We're at integration tests, the 20% volume mark. This is where we finally start connecting components together.
Right. Integration tests really only become meaningful for larger systems composed of many independent services or components.
And their function is not to retest the business rules.
Correct. We've already proven those are correct in the component layer. The job of an integration test is to ensure that the different components communicate effectively with each other.
We're finally testing the plumbing of the application.
Absolutely. Our sources call them choreography tests or plumbing tests. They ensure that component A sends a message in a format that component B actually expects.
And that component B can correctly interpret it and act on it.
Exactly. It's all about ensuring the contracts between your services are upheld and that the data flows smoothly through the system as intended.
Okay, if we are assembling groups of components, how does isolation work here? We're not bringing up the entire system yet, are we?
No, not at all. We still practice isolation where it makes sense. For a given integration test, we assemble the specific group of components whose communication we want to verify.
And everything else.
Any components outside that specific group, say, a long-term archival service or an external tax calculation API, those are still decoupled using mocks or test doubles. We focus only on the quality of the interaction between the tested group.
Who typically owns these tests? And why does the volume drop again to just 20%?
These are structural architectural tests, so they are typically written by system architects or lead designers, people who have a comprehensive bird's-eye view of the entire system's assembly.
And the volume drops because?
The volume drops because the number of possible interactions between components is much smaller than the number of components themselves, and it's exponentially smaller than the number of internal functions inside those components. You're testing the seams, not the fabric.
What's the runtime implication for these? Are they in the main CI loop?
Generally, no. They are slower than unit or component tests because they involve more processing, more layers, even if some dependencies are mocked. So they are often not part of that rapid CI loop that runs on every single check-in.
So when do they run?
They might be run periodically, say, on an hourly build or a nightly build or even weekly for very large systems. The key is finding a schedule that still provides timely enough feedback on the structural integrity of the system.
Okay, that takes us to the highest automated layer. System tests at the 10% volume mark. This is the ultimate end-to-end integration check.
It is. System tests are automated tests that are executed against the entire integrated system. All the pieces are there. When a user interacts with the UI, these are often the kinds of tests that are mimicking that interaction, using tools like Selenium or Cypress.
And their job is to ensure the whole thing is wired together correctly.
Yes, that its parts interoperate according to the overall deployment plan.
So if a business rule fails here, it's a huge problem. But our sources are adamant that system tests should not test business rules. Why is that?
It goes back to that diagnostic cost we talked about. If the Add to Cart button fails in a system test, where is the defect?
It could be anywhere.
Exactly. Is it a bug in the UI rendering code?
Right.
Is the API call structured incorrectly? Is the logic in the cart component service broken? Or is the database connection timing out? The failure is completely ambiguous and debugging becomes a nightmare.
So if you discover a logic failure at this high level, it means your component tests failed you.
Your process has already failed. The defect should have been caught much, much lower down.
So what are system tests primarily focused on then? It's not business logic.
They are focused on two main things: verifying the complete assembly of the system and testing its performance characteristics.
So this is where performance testing lives.
Exactly. This is where we run our throughput and performance tests. We check latency. Does the response come back in under 200 milliseconds? We check load. Can the system actually handle 10,000 concurrent users? We check resource consumption, memory usage, things like that.
So these tests aren't about internal correctness, but about external robustness and performance under real-world conditions.
That's it. And that 10% volume limit, that is a necessary discipline to protect the team from slow builds.
Because they're the slowest of all the automated tests.
By far. They're the slowest and most brittle tests in the entire suite. If you try to cover 50% of your business logic here, your test suite will take hours to run, which completely destroys your developable feedback loop and velocity. The 10% limit ensures we only verify the most vital paths of system construction and the key performance metrics, trusting all the lower layers to guarantee the behavior.
Okay, so we've automated 95% of our testing with this pyramid structure. We have gone from the intent of a single line of code all the way up to system assembly and performance validation. That brings us to the very apex, the final 5%. Manual exploratory tests.
This is where we pay the QA characterizer to use their highly valuable creative human brain.
And this is the critical layer that automation can never, ever replace.
It can't. These tests are defined by being unscripted and unautomated. They rely on human interaction, on creativity, and on the ability to spot anomalies that no pre-written script would ever look for.
You said unscripted. Why is a written test plan actually antithetical to good exploratory testing?
Because a plan, by its very nature, limits the scope of your investigation to the known requirements and expected paths. The entire intent of exploration is to discover unexpected behaviors.
Right.
It requires the tester to continuously design and execute new tests on the fly based on the system's immediate response. If a written plan exists, the tester just becomes a compliance checker, not an explorer. They're following a script.
It's about thinking like a confused user, or maybe even a slightly malicious user. Someone who clicks buttons in the wrong order or tries to break things based on intuition.
It's true behavioral characterization. For example, a tester might try to see what happens when they trigger a known error state, say, entering an invalid password 5 times and getting locked out.
Okay.
And then they might rapidly try a successful action like a password reset before the account-locked error message fully renders or the back-end state has settled. They're looking for those weird state transitions that the developers never specified or anticipated.
Or race conditions.
Yeah.
But what happens when you copy and paste a weird string of Unicode characters into a text field?
All of that. Those are the subtle peculiarities that can crash an application or expose a security vulnerability in production.
So how do professional teams structure this bug hunting effort to really maximize that unique human input?
Many of the best organizations schedule specific time-boxed events. Sometimes they're called bug hunting bangs or testing parties.
Okay.
These are dedicated periods, say 2 full days before a major release, where they pull in a highly diverse group of participants to just use the system.
And when you say diverse, you don't just mean more testers.
No, absolutely not. You want people who are not the core developers or testers. Bring in the product managers, the documentation writers, sales representatives, even executive assistants, people who use computers in fundamentally different ways and have different cognitive biases.
That's brilliant. That brings in genuine real-world variability. A programmer will naturally interact with this system in a linear, logical way, expecting certain responses.
Hmm.
A non-technical user will just click on things based on visual intuition.
Precisely. And the goal of these bangs is not to cover every single business rule that's already been done by the 50% component tests below. The goal is sheer peculiarity discovery.
You're stress testing the usability and robustness against unpredictable human behavior.
Exactly. You're ensuring the system behaves well when subjected to that chaos across all execution pathways. It gives you that final, invaluable layer of confidence before you release to the public.
This entire strategy really reveals that quality assurance is fundamentally an architectural discipline. It's applied at every single layer, not just some final stage you bolt on at the end.
That is the key takeaway. That's the synthesis. Test-driven development is a non-negotiable discipline for enforcing and expressing requirements at the code level. But TDD is only one part of a powerful, total testing strategy.
And that total strategy requires that complete hierarchy. The unit, component, integrations, system, and exploratory tests. Each one contributes maximum value for the minimum cost and runtime.
And if you're missing any of those tiers, especially those critical middle layers, the component and integration tests, the pyramid loses its structural integrity, and you are guaranteed to regress on that core goal.
The goal of QA finding nothing.
Yes. If your unit tests are great, but you lack component tests, you've verified that your engine parts work, but you have no idea if the assembled engine actually performs the business function of propulsion.
And we really have to emphasize the urgency here. For this whole structure to remain, as the methodology demands, continuously clean, these tests must be run as frequently as possible.
To ensure maximum feedback speed, the feedback latency has to be minimized. Unit and component tests should run continuously on every save or commit. Integration tests, maybe nightly, system tests, periodically.
That synergy is what ensures that quality is built into the system's DNA from the very first line of code.
And it prevents simple defects from ever becoming those expensive, painful integration problems down the line.
Let's just bring the two QA roles back into the structure one last time, just to really cement the concept for everyone listening.
Great idea. The specifier role ensures the foundation and the middle of the pyramid are strong. By working with the business to define those component tests, they ensure the entire system is designed around the core business value proposition. They are defining success.
And the characterizer role focuses on the unique value of the apex. They use human ingenuity to discover the unknown unknowns, providing a safety net that automation simply cannot cast.
They are verifying reality.
The combination seems unbeatable. It really does transform QA from what can be seen as a costly checking function into a core architectural and product definition function.
It absolutely does.
Okay, so final thought. If the goal is truly for QA to find nothing, we need to think about where most organizations fail and what the resulting measurable symptom of that failure is. What is the single most common layer of this pyramid that organizations, especially those that are maybe just focused on TDD and then some slow UI testing, tend to skip?
It's almost always the middle. It's the component tests and, to a lesser extent, the integration tests.
So they have the bottom and the top, but nothing in between.
Exactly. Organizations are often TDD compliant at the unit level, which is great. And then they jump straight to writing those slow, fragile system or UI tests at the top. They completely neglect the rigorous, fast verification of isolated business rules that you get from component tests.
They build the engine parts, they build the full car, but they never test the engine on a stand by itself.
A perfect analogy. They connect everything in one massive, slow, high-level test run. They build that ice cream cone.
And what's the measurable symptom of skipping those middle layers? How can you know for sure you have this problem?
Look at your build time. If your main continuous integration build, the one that runs all day long, takes longer than, say, 15 minutes to give you a green or red light,
Yeah.
you have statistical proof that you've built an ice cream cone instead of a pyramid.
And that's the smoking gun.
It is. You are relying too much on slow, high-cost tests, and that structure will compromise your ability to ship clean code rapidly every single time. That gap in the middle, that's precisely where the horror begins, because that's what allows defects to make it all the way to the surface where they are exponentially more painful and costly to diagnose and fix.
That provides such a tangible, measurable call to action for our listeners. Look at your test architecture, look at your CI pipeline speed, and ask yourself honestly if you've built a true pyramid designed for continuous quality. Thank you so much for diving deep with us today.
My pleasure. This really is a framework that can change how organizations think about building quality software.
We'll see you next time on The Deep Dive.